All right, folks, up until this point, we've looked at a couple of things. We've concerned ourselves with Kirchhoff's voltage law, Kirchhoff's current law, and then also basically the application of combined resistances in which we actually gain equivalent resistance through series or parallel types of networks. So what we're going to look at today are a few of the applications of what we call voltage division. Now, voltage division is really a tool that we use that basically applies Kirchhoff's voltage law, but instead of actually going through and finding currents and then multiplying those currents by the resistance, by Ohm's law, in order to gain that voltage, we can actually utilize a tool derived from KVL in which we can just go ahead and find those voltages directly with only resistances. Now, again, voltage division is a direct method of determining voltage without a current, and it's directly derived from Kirchhoff's voltage law. Sum of all voltages around a closed loop are equal to 0, or the sum of voltage drops equals the sum of voltage rises. And so we're actually going to derive this tool up front. You know, lots of what we do in this class, we do derive for you guys how these tools are actually formed so that you guys can actually see that it's not just coming out of thin air in the book. So we're going to derive this first, and then we're actually going to take basically a single series element circuit, and we're going to just keep expanding it out to where we can see how voltage will actually continually divide throughout the circuit, and a couple of applications of the series and parallel relationships. So let's take a look at a very, very simple series circuit and see if we can get some understanding first of finding the voltages individually while using currents. So here we got voltage source. Now lots of what we're doing in here is symbolic today. But Vs, voltage rise, negative to positive, in which by passive sign convention, remember that current will leave the positive terminal of the source and then go into the positive terminal of the resistance. Again, that's when we actually signify positive to negative, where the current moves from a higher potential to a lower potential. Remember, we say that because as that current moves through the resistor, it's actually losing energy. It's taking energy actually to get that current through that element. So positive to negative for the potential difference across R1 for the voltage, and then R2 and R3, positive to negative for VR2, and positive to negative for VR3. Now, how do we know that these are series, you might ask? Well, going back, always start off labeling your nodes, and when we label our nodes, we can then apply our understanding of series and parallel in order to actually, make sure we remember here that these elements are definitely in series with each other. Here we got Vs and R1. Those are separated by one single common point of contact. R2 and R1 are in series because R1 and R2 share one single point of contact. R2 and R3 are also in series because they share one single point of contact. And then finally, R3 and Vs are in series because they share one single point of contact. And as I've said before in a prior lecture, here all of these we say are effectively in series with each other because these series elements all have a series relationship with their adjacent element. So again, here sum of voltage drops equals the sum of voltage rises, and by KVL, going around this closed loop here, the drops VR1 plus VR2 plus VR3 would equal the voltage rise. We only have one voltage rise here with one source, so that's going to be equal to Vs. So what we have done before in the prior lecture was actually we went through and found these individual voltages individually because we went through and expanded this by Ohm's law for each element, and then we were able to take that current that we found and then just multiply that by R1, or take that current, multiply it by R2, take that current, multiply it by R3, and therefore we got basically the voltages for each element by just applying Ohm's law. But what if I don't want to find the current? What if today I just woke up this morning and, sitting there drinking coffee in the morning, just decide I don't care about current today and a flow of charge. Not really worried about it. Maybe I could develop a tool that would allow me to find those voltages directly and not worry at all about the current. Well, let's see what we can do here. Well, I took the KVL equation here, VR1 plus VR2 plus VR3 is equal to Vs. I went ahead and expanded that by Ohm's law for each element. Now remember, series elements, they have the same current, different voltages. So here, our common variable is I. R1 times I plus R2 times I plus R3 times I, and that's equal to Vs. But yes, factoring out I, sure enough, we get R1 plus R2 plus R3. Remember? Look at that. Equivalent resistance for series elements. Yes. R1 plus R2 plus R3. That's where that came from. That's where the equivalent resistance for series elements actually came from, was actually from this expansion right here. And we went through that in a prior lecture, but just reviewing it a little bit right now. Well, the first thing we want to do is go ahead and find how we derived the current in the first place. All we had to do was divide through by R1 plus R2 plus R3, divide that into Vs, and then that means that that current we actually would find directly by the application of KVL and Ohm's law. So if we took this form right here, and we know that VR1 is equal to R1 times I1, what if we substitute this in for I? And so if we substitute that in for I, then we get R1 times Vs over R1 plus R2 plus R3. Well, if we go ahead and pull Vs out of the bracket and put R1 into the bracket, oh, look at this. Then VR1 is equal to Vs times what is really the ratio of R1 over R1 plus R2 plus R3. And in this case, guys, if we look at the units here, units of ohms in the numerator and ohms in the denominator, the ohms cancel each other out, and so all we're left with is basically volts. So, in fact, actually, voltage division, once derived in this form, basically states that the voltage across an individual element is basically going to be directly proportional to that element's resistive value over the summation in that series loop of R1 plus R2 plus R3. Now, if we look at VR2, same thing. We go ahead and just substitute in what we found up here for I. So R2 times I is equal to R2 times Vs over R1 plus R2 plus R3. Sure enough, we factor out basically Vs, put that over outside the bracket, put R2 back into the bracket, and sure enough, we get the same thing here. VR2 is equal to Vs times R2 over the summation of those resistive elements. Now, same thing with VR3. Instead of actually putting in R2, now we're looking for R3 times I. Go ahead and substitute what we have for I, and then we get basically Vs times R3 over R1 plus R2 plus R3. So voltage division works for any number of elements in series. Any number of elements in series. But let's prove this. Let's prove that this actually works by looking at the original method and then basically just substituting that current value that we find, multiply it by the resistance. Let's see if voltage division actually works. So, small little example here. 30 volts over on the left side, and then we got resistive values of 14, 10, 13. Uh-oh, I didn't show that they were in series, but yep, we got a node here, got a node here, here, and here. So sure enough, we see that all of these elements are effectively in series with each other. So if I find the current by taking 30 volts and dividing it by the summation of the resistances, 14 plus 10 plus 13, we come up with a current of 0.8108 amps. But to find the voltage Vx across that 10 ohm resistor, all we have to do is take that current of 0.8108 amps and multiply that by the resistance of 10 ohms. And sure enough, we get 8.108. Or did I say 8.1? This is 0.8108 amps. Maybe I didn't say that before. Whatever. So here, multiplied by the resistance of 10 ohms, and we get 8.108 volts. Let's see if that works with voltage division. Sure enough, Vx is equal to 30 volts multiplied by 10, divided by 14 plus 10 plus 13 in the denominator, and sure enough, this calculation gives us 8.108 volts. Sure enough, guys, boom. Voltage division does work. And it works again for any number of elements in series. Let's go ahead and start expanding out this type of circuit and start applying different ways that we can maybe even find, voltage across maybe two parallel elements. See if that can give us a little bit of clarity in using voltage division in different manners. So remember all of the work that we've done up until this point in breaking down the circuit to find equivalent resistance. Well, now we're going to start doing that. We're going to start applying those concepts of equivalent resistance. So let's move over down to the next section of the board. All right, so we're just going to expand out what we just did and just go ahead and see if we can start solving circuits that are a little bit more complex. So here, I just decided to tack on a fourth resistor. And that resistor is actually in parallel with R2. How's it in parallel? Well, here we got the node that connects R2 to R1, R2 to R3, but since there's nothing in between R2 and R4 on the top and bottom, then we can say that this entire section on the bottom here and on the top, this is one single common node, and that's one single common point of connection. It's just a piece of wire with no resistance. So therefore, R2 and R4 actually share two common points of connection. It means that they're in parallel. And parallel elements have the same voltage, different currents. But also look here too, guys. R2 is no longer in series with R3 because of R4's connection. And R2 is no longer in series with R1 because of that R4 connection. But we want to find VR4, and we could also find basically VR2 if we wanted to. So let's go ahead and just make sure that we understand too that VR2 is equal to VR4 and also equal to the voltage that we find across their equivalent resistance. The voltage across each of these individual elements is the same as the voltage across that equivalent resistance when we break it down. And if we want to break that down, sure enough, REQ, the equivalent resistance of those two parallel branches, is 1 over the summation of the reciprocals, or 1 over R2 plus 1 over R4. And sure enough, we break the circuit down. I always say right now, redraw the circuit as you go. Gives a map of basically your calculations that you're doing, so you can go back and basically be able to look through and see how you've actually started analyzing the circuit. And sure enough, bam! Once we actually break down the two parallel elements, now we got a single series loop. And once we have that single series loop, we can actually apply the fact that VREQ by voltage division would just be equal to Vs times REQ over the summation of 1 over R1 plus 1 over REQ, the equivalent resistance, plus R3. So the voltage across R4 or even R2 is really dependent upon their parallel equivalence. Okay? Their parallel equivalence. And once we actually break it down to that parallel equivalence, then we can use voltage division, but instead of using R2 or R4, we have to put in the value of that equivalent resistance in the numerator. And in the denominator, in the summation of those resistances now, we have to put in REQ at the bottom here. So let's see if we could apply this with actual numbers here. And so two parallel elements, we're going to put 3 parallel elements. So 15 in parallel with 20 in parallel with 25. So let's find the voltage across the 20 ohm resistor. Well, this one's quite easy to do. Here we got 3 parallel elements. Now remember, when finding that equivalent resistance, what it is for 2 elements in parallel, we can also go ahead and do 3. So 1 over the summation of the reciprocals, 1 over 15 plus 1 over 20 plus 1 over 25. That gives us an equivalent resistance of 6.38 ohms. Okay, 6.38 ohms. So V20 is equal to V25, which is equal to V15, the voltage across each of these elements, because sure enough, just like in the derivation up here, symbolically, these elements share two common nodes. None of these elements have anything in between at the top or in at the bottom. So V20 is equal to VREQ, which is just equal to 50 over 6.38 over 10 plus 6.38 plus 12. So So 50 times 0.2249 or 0.225 gives us a voltage of 11.24 volts. Now, I want to make sure that's clear again. Parallel elements have the same voltage, but their equivalent resistance has the same voltage as well. The equivalent resistance has that same voltage, and so we have to make sure that when we're looking at those individual voltages that we understand that once we've actually broken down the circuit and found that equivalent resistance, all we have to do is just find the equivalent resistance of that element. And then for this type of network, it's done. Done. Yeah, we got the voltage across R4 and also across R2. Well, what about if we have a branch here that actually has elements in series in it? How do we actually have to do that? Now, in prior examples for this class, we definitely have shown how to break down equivalent resistive networks with series and parallel elements, and also basically series elements within basically a branch that's parallel to another resistance. Let's see if we can maybe start applying those concepts in order to actually start doing more analysis, more complex analysis. So let's do a third example. Yep. Apologize, this is seems like my stand's a little bit kind of wonky today. All right, so for this one, got R2. I'm going to put another parallel branch over here, but that parallel branch will include two series elements, separated by one common point of connection. Now, the thing that I want to really point out to you guys is that the voltage, if we look here, these two elements are in series with each other, but that combination, R3 plus R4, because that series relationship, is in fact in parallel with R2. The bottom node of R4 is the same as the bottom node of R2. The top node of R3 is the same as the top node of R2. So in fact, actually, these two series elements, their combination is in parallel with R2. So the voltage, it would suffice to say that the voltage across R2 is also the voltage across both of these elements together. And if we have a voltage across two elements that are in series, that means that the individual voltages by series relationship is different for each of these elements right here. So the voltage across R3 has to be different from the voltage across R4 because of this series relationship. So what that really means for us, guys, is that whatever voltage that we find between these 2 points, these two common points here, remember, voltage is potential difference, and that potential difference can exist between any 2 points within a circuit, any 2 points. And so here, that voltage exists across R2, but what this really means is that once we find this voltage, that voltage is then going to divide again between R3 and R4. So we actually have to find the voltage first across R2, or the equivalence of this whole network here, and then we actually have to perform voltage division not once, but twice. So let's first find the equivalent resistance. So Req is equal to 1 over the summation of 1 over R2 plus 1 over R3 plus R4, because this right here is the series relationship, series equivalence of these two together. And once those two combine together, then that equivalence is in parallel with R2 directly. So here, 1 over R1 plus 1 over R3 plus R4. But the voltage across basically R2 is the same as the voltage across the equivalent resistance, but that voltage here is made up of the individual voltages in series of R3 and R4. So basically what happens here is that the voltage from the source divides between R2, this equivalence between these 2 points, and also R3. But then this voltage that's found between these 2 points here then divides again between R3 and R4. So voltage divides not once, but twice with these 2 points here. So let's take a look. So if we go ahead and finish our analysis, here we found the voltage across R2, which we know is also the voltage across the equivalence of basically these 2 elements to get combined together in series, which then is in parallel with R2. So VREQ is equal to VR2. We find that by simple voltage division. VS times REQ over R1 plus REQ plus R3. Then that voltage then divides again. And we can find that for R4 and also for R3. So we take this voltage here, and that voltage that we find is now the new voltage that actually divides between R3 and R4. So VR4 is equal to VREQ over R4 plus R3. VR3 is equal to VREQ times R3 over R4 plus R3. So here's the thing. This section of examples that we're going through is in fact actually a step into basically solving more complex circuits. I call this essentially cascaded voltage division. Essentially, voltage starts dividing throughout an entire network. And we're going to see in the next lecture how current's going to do the same thing as well. But if you understand the concepts in example 1, 2, and 3, it doesn't matter how much more large these networks actually grow. If you can break down the circuit and then be able to identify where voltages actually divide, then basically solving more complex circuits is not conceptually harder. It's just a little bit extra work. So we're going to continue to look through examples like this and make sure you guys get enough practice so you can actually see how to apply these concepts, because as we start going throughout the rest of the class, we're going to be holding on to these concepts throughout the class. And for those of you who are electrical engineers, you're going to go on and hold on to these concepts for basically the rest of your career. So we're going to keep working examples on these, like usually the start of this class, the initial concepts, and so you see we're applying throughout here, all these initial concepts, and sometimes those get a little bit confusing. Basically being able to identify elements and relationships to each other, and then understanding how to apply KVL and KCL throughout an entire circuit network. It's a little bit difficult, but we're going to get you there, and then we're going to be able to start utilizing cooler central processes for analysis techniques. So I'll see you next time.